In this video, I will show you how to find the resultant vector when two or more vectors are acting together. Now the key is organization. So you're going to want to use this chart for every problem. Now in this problem, the two vectors that are working together are the velocity of the running and the velocity of the throw. And we are to figure out what the resultant velocity is. In the first row, we will record the magnitude and direction of each vector. And in the second row, we will convert to component form, the horizontal and vertical component of each vector. So as far as the running, the quarterback is running forward at 5 meters per second. So that 5 meters per second is the magnitude. So I'm just going to put MPS for meters per second. And he throws the ball with a velocity of 25 meters per second. So there's your magnitude right there. The magnitude of the velocity of the throw is 25 meters per second. So now we need to talk about the direction of the running and the direction of the throw. Now some students will get confused when you are trying to talk about direction, but the problem does not say anything about north, south, east, or west. So the key is basically you can pick whatever direction you want and just stick with it. So the problem just says that the quarterback is running forward. So in my mind, I'm picturing the quarterback sort of running from left to right across my screen. So I'm going to go ahead and imagine that the quarterback is running east. Now if you had him running west or north, that's fine. Just pick a direction and stick with it. Now a vector like this is on the positive x-axis. So that is actually 0 degrees if you're measuring from the x-axis. So for the purposes of this chart, I will say the magnitude of the running is 5 meters per second at a direction of 0 degrees, flat horizontal, to the east, let's say. Now let's talk about the direction of the throw. So the problem says that the throw makes an angle of 40 degrees with the horizontal. So, the idea is he's throwing in the same direction that he's running. So his throw, 40 degrees with the horizontal, I'm picturing that it's doing like this, where this is the 40 degrees. Okay, so that is what we will put on the chart. Direction of 40 degrees. So we had 0 degrees and 40 degrees. Now, that's the magnitude and the direction for both vectors. We need to convert these into component form, x comma y, so that we can add them together. A horizontal vector, like the running vector, you don't need any calculator or anything like that to put this into component form. The entire 5 meters per second is the horizontal component. So I'm going to just go ahead and put that 5 meters per second as the x, because that is the horizontal component. There is no vertical component, so we'll just go ahead and call that 0. If he had been going to the west, I would have called this -5, but let's just leave it like it is. Now, on the other hand, with this 40 degrees, I need another way of converting this into component form. And here's how. We're going to use a little formula. If I know the magnitude r and the direction theta that's being measured from the positive x-axis, the way this one is, I can find the horizontal component by doing r cosine theta, and the vertical component by doing r sine theta. So that's what I will do right here. So our cosine theta would be 25 cosine 40, and our sine theta would be 25 sine 40. And you just put this in your calculator. So the horizontal component is 19.15 and the vertical component is 16.07. So I'll just go ahead and record that on my chart. Now, since I have component form, I can just add these two vectors together to find the resultant. So I can just add the horizontal component with the horizontal component and the vertical component with the vertical component. So that's 24.15 for the horizontal component and 16.07 for the vertical component of the resultant vector. So we want the overall magnitude and direction of this throw. So we need to take this component form and turn it back into a magnitude and direction similar to this. So we can calculate that off to the side, starting with the magnitude. For the magnitude, we can just do the magnitude formula. So we're doing 24.15 squared plus 16.07 squared. Take the square root of all that in your calculator. So that means the overall speed of the throw, including the speed given to the throw by the running, is 29.01, and what were the units? Meters per second. Okay, so you can see that that is a little bit faster than that. If he was standing still and just threw the ball, it would be traveling at 25 meters per second. But with the running, now it's 29.01 meters per second. Okay, now the direction. Alright, we can calculate the direction off to the side as well. Looking at the components, we are obviously talking about the first quadrant. Alright, we have a positive horizontal and vertical component, so just imagine that this vector is in the first quadrant, and we can break it down into its vertical and horizontal components. Horizontal component being the 24.15 and the vertical of 16.07. With those numbers, we can find this reference angle R. Actually, I guess I don't have to call it a reference angle because this is the actual angle that we're looking for. So I'll just call it theta. Now the tangent of angle theta should equal 16.07 over 24.15. So I should be able to find the direction by doing the inverse tangent of the fraction. Go ahead and use a calculator. So the direction of this resultant vector is 33.64 degrees with the horizontal. Alright, and that is the final answer right there. Okay, let's look at the next problem. A ship sails 50 miles with a direction of north 20 degrees east, and then turns and sails 30 miles with a direction of north 80 degrees east. Find the ship's resultant distance and direction. Well, it's time to get organized. Bam! You're definitely going to want to use a chart like this. Now, this is a displacement problem, which means that we have two short trips, which I will call trip 1 and trip 2, that combine to form the overall trip, which I will call the resultant. In the first row, I will record the magnitude and direction of each trip, and In the final row, I will convert to component form with the horizontal component and the vertical component. So, magnitude and direction of trip 1 and trip 2. A ship sails 50 miles. Boom! That's the magnitude. 50 miles. Now the direction, this is a little weird. North 20 degrees east. Let me just write that down and come back to it in a moment. North 20 degrees east. Let me come back to that. Then he turns, well, there's no he, it's a ship. Then turns and sails 30 miles. Boom, that's the magnitude. 30 miles. I forgot the units. 30 miles. With direction north 80 degrees east. Okay, so north 80 degrees east. So we got the magnitude easily. Now let's go back and talk about this direction. For trip 1, we're told that the direction is north 20 degrees east. Now, what does that mean? North 20 degrees east means start at north and turn 20 degrees in the direction of east. So this is a 20-degree turn. So this vector is here. Now, for the chart, we need to describe the direction as a turn that starts from the positive x-axis and turns counterclockwise. So we need this angle theta. These are obviously complementary, all right? They're sitting here in the first quadrant. They have to add up to 90. So if this is 20, then theta must be 70 degrees. But 70 degrees is what we need for the chart. Okay? This direction in these two boxes of the chart always have to be measured from the positive x-axis. So let's do the same thing for trip 2. The direction of trip 2 is north 80 degrees east. So again, that means start at north and turn 80 degrees in the direction of east. Alright, so the vector is here if this is 80 degrees. Well, if that's 80 degrees, then this angle measured from the positive x-axis must be 10 degrees. And it's the 10 degrees that I need for my calculations on the chart. So that's what I'm going to put right here, 10 degrees. So we have the magnitude and direction for each leg of the journey. Unfortunately, there's no way to just combine the magnitude and direction to get the resultant magnitude and direction. That's why we have to take this middle step and convert these to component form so that we can add them together. So the way you can take magnitude and direction and get component form is using this tiny little formula. If I do r cosine theta, that's going to be the horizontal component. If I do r sine theta, that's going to be the vertical component. So that is what I'm going to do. So for trip 1, r cosine theta is 50 cosine 70. And r sine theta is 50 sine 70. This is something you can put in your calculator. So the horizontal component is 17.10 and the vertical component is 46.98. And we just record that on the chart right here. Now for trip 2, r cosine theta is 30 cosine 10. r sine theta is 30 sine 10. Calculator again. The horizontal component is 29.54 and the vertical component is 5.21. And we'll record that right here on the chart. Now, with component form, if you want to find the resultant, all you have to do is add the two vectors together. Just add the horizontal component with the horizontal component and the vertical component with the vertical component. So, the resultant vector has a horizontal component of 46.64 and a vertical component of 52.19. But what we really need is the magnitude and direction, similar to what we had for trip 1 and trip 2. So we can get that. We can calculate the magnitude. All right, let's just do that off to the side. We'll use the magnitude formula. So we'll do 46.64 squared plus 52.19 squared. Do the square root in your calculator. 0.64 squared plus 52.19 squared. That's 69.99. That means the total trip had a distance of 69.99 miles. That's the magnitude. But we also want the direction. Let's see. For the direction, notice that we are in the first quadrant. The horizontal component is positive and the vertical component is also positive. That puts us in the first quadrant. Let's record the horizontal and the vertical component in the graph. So that's 46.64 and 52.19. We can use this to find the direction theta, because the tangent of theta should equal 52.19 over 46.64. Then the angle itself will equal the inverse tangent of 52.19 over 46.64. Calculator. So the direction is 48.21 degrees. Now, sometimes that is the direction that we want. But in this case, we cannot use this for the final answer for one reason. Your final answer has to give the direction using the same format that was used in the original problem. So in the original problem, they did not just give us an angle measured from the east counterclockwise. They gave us a direction like north 80 degrees east, this type of format. So how can we take 48.21 degrees and write it as something like north and some kind of degrees east or something like that? Well, there's two ways we could do it. If I wanted to use the angle that I already have, I suppose we could say, we could look at this position as starting from the east. Then if you turn 48.21 degrees towards the north, then you're there. So that's one way that we could describe this. East, 48.21 degrees north. Now, however, I'm looking back at the directions that they gave. Both of them started with north. North 80 degrees east, north 20 degrees east. So it would be nice to record the direction in the same way starting from north. So let's figure out what this angle is so we can find out how far we have to turn from north. Now these two angles should be complementary. So I should be able to find the other angle by doing 90 minus 48.21. I decided to call this angle B, and angle B is 41.79 degrees. Now angle B we can look at as starting from north and turning 41.79 degrees towards the east. So that's why this direction would be written north 41.79 degrees east. So this is probably the best direction to use in your final answer for this problem because it really matches what was given to us in the original problem. So north 41.79 degrees east. And that's it. That's the final answer. Let's go ahead and do one more problem. Alright, this problem is very similar to the problems that we've already done. So I encourage you to pause the video and try to do this problem by yourself first. A plane flies 200 miles per hour with a direction of north 40 degrees west. The air is moving with a wind speed of 60 miles per hour at a direction of south 10 degrees west. Find the plane's resultant velocity and direction. Let's get organized. So let's see. We've got the two vectors, the velocity of the plane and the velocity of the wind. And we are being asked to find the resultant velocity. In the first row, we will record the magnitude and direction of each vector. In the second row, we will write the component form of each vector with the horizontal component and the vertical component. So for the plane flies 200 miles per hour. That is the magnitude of the plane's velocity. So let's go ahead and write that down. 200 miles per hour. Now the direction, they're giving us this north 40 degrees west business. We're going to have to change that in order to be able to use it on this chart and in our calculation, so let me come back to that. The air is moving with a wind speed of 60 miles per hour. There's your magnitude, 60 miles per hour. Now the direction is south 10 degrees west. That's not something that I can put in my calculations. So I'm going to have to convert that to something I can work with. South 10 degrees west. So let's deal with these directions. So they gave us the direction of the plane as north 40 degrees west. Let's remember what that means. The north means you start at north and then you turn 40 degrees in the direction of west. So I'm going to start at north, I'm going to turn 40 degrees towards the west. So this is 40 degrees right here, so this is the position of the vector. Now for our calculations on this chart, we are going to need the angle as measured from the positive x-axis. Call it theta. So that should be 90 degrees plus the extra 40 degrees. So that's why theta is going to be 130 degrees. This is the angle that we will need for our calculations. So always use the angle measured from the positive x-axis. Okay, let's do the same thing with the wind. So the wind direction is given as south 10 degrees west. So that means start at south and turn 10 degrees towards the west. So this is 10 degrees and the vector is here. Now we need to find this angle theta measured from the positive x-axis. So this angle should be 270 minus 10. Alright, look at it closely. This angle was on its way to being 270 degrees. If it had made it all the way to the south arrow, that would have been 270 degrees. But it had to stop short by 10. So 270 minus 10. So of course that means theta is going to be 260 degrees. That's the angle that we will need for our calculations. Okay, so now we've got the magnitude and the direction of each vector. But what we really need is component form, because there's no way to directly combine these magnitudes and directions to come up with the magnitude and direction of the resultant vector. So we have to go indirectly by converting them to component form first. The way we can do that is by using this tiny little formula. If I do r cosine theta, that's going to give me the horizontal component. If I do r sine theta, that gives me the vertical component. So for the plane magnitude and direction, r and theta, r cosine theta is 200 cosine 130. R sine theta is 200 sine 130. Calculator. So the horizontal component is negative 128.56 and the vertical component is 153.21. And we will record that here on the chart. And of course we will do the same thing with the wind. R cosine theta is 60 cosine 260 and r sine theta is 60 sine 260. Calculator. So the horizontal component is negative 10.42 and the vertical component is negative 59.09. And we record that on the chart right here. Now that we have component form, we can find the resultant vector by adding these vectors together. We can just add the horizontal with the horizontal and the vertical with the vertical. So the resultant vector has a horizontal component of negative 138.98 and a vertical component of 94.12. But what we need is a magnitude and direction similar to this. So we can calculate that off to the side. Let's start with the magnitude. We can find the magnitude using the magnitude formula. So we will do negative 138.98 squared plus 94.12 squared. Do the square root of all that in your calculator. So the magnitude is 167.85. Now in the context of this problem, that means that the overall speed of the plane is 167.85 miles per hour. Now let's find the direction. Notice that the horizontal component is negative while the vertical component is positive. That means on this graph we are left and up. So we're in the second quadrant. So go ahead and draw your vector into the second quadrant. And now let's break that apart into its vertical and horizontal components. So the negative 138.98, that's our horizontal component, and the 94.12, that's the vertical. So using these numbers, we should be able to find the measure of this angle R, the reference angle, because the tangent of angle R is going to be 94.12 over 138.98. Notice I'm ignoring the negative sign. That's because I just want the positive value of R. So the measure of angle R will equal the inverse tangent of the fraction. Calculator. So the reference angle R is 34.11 degrees. Now we have to be very careful about how we write the direction in our final answer. Sometimes we measure an angle from the positive x-axis going counterclockwise like this. But you want the direction that you give in your answer to match the way they gave you the direction in the original problem. So in the original problem they gave us things like north 40 degrees west, and south 10 degrees west. Notice that they're starting with either north or south. So we should do the same thing. So we really want to start at north and then say how many degrees do we have to turn towards the west to get to the vector. So we can write the direction the same way that they did. So these angles will be complementary. I'm going to call this angle B. You know what? I'm going to call it Q. Alright, because Q and R are consecutive letters. So these are complementary, so angle Q should equal 90 minus 34.11. So angle Q is 55.89 degrees. So I could describe this direction as starting from the north and turning 55.89 degrees towards the west. So again, we would write that as north 55.89 degrees west. So that's how I will write my final answer. Let's put a box around it, because that's it. If you like it, then you should have put a box on it. If you like it, then you should have put a box on it. Now, technically, I suppose it would have been also okay to say, describe this position as starting from the west and then rotating the 34.11 degrees towards the north. Okay, using the reference angle R instead. So technically we could have written it this way, but I think the preferred method is to start from either north or south.